Hi, I'm Wu Gong from Lehigh Harvard Institute, University of Minnesota. In this talk, I'm presenting our tool Proformer, a hybrid Macaron transformer model that predicts expression values from DNA sequences. Our method won the third place in the final leaderboard. The breakthrough high-throughput measurement of the cis-regulatory activity of millions of randomly generated promoters provides an unprecedented opportunity for us to systematically decode the cis-regulatory logic that determines the expression values. In this dream challenge, we developed an end-to-end transformer encoder architecture, Proformer, to predict the expression values from DNA sequences. Proformer used a Macaron-like transformer encoder architecture where two half-step feed-forward layers were placed at the beginning and the end of each encoder block. A separate one-dimensional convolution layer was inserted after the first feed-forward layer and in front of the multi-head attention layer. We tested two architectures at the top of the transformer, global average pooling and the multiple expression heads with mask filling. Global average pooling layer at the top of a neural network is commonly used for the regression and the classification tasks. However, we found that when applying the global average pooling layer at the top of a large transformer models, for example, with dimension size of 256 and the block size of 8, the whole model sometimes failed to converge on training on relatively small amount of data. In order to address this issue, we proposed a new design where the model predicted multiple expression values through multiple heads and takes the average of all predictions as the final one. At the same time, the model also tries to predict the randomly masked DNA nucleotides. In order to systematically compare the performance of two designs, global average pooling versus multiple expression heads with mask filling, we trained the model on 10% of the training sequence expression pairs provided by the organizers. Then we evaluated the performance on 2% of the data. For multiple expression heads, we also examined their performance over a different number of heads, ranging from 1 to 64. Overall, we found that the expression heads with mask filling gave better performance than global average pooling. The best performance was achieved at dimension size of 128 and the Macaron block size of 8. We can also see that as the model size becomes larger and deeper, the global average pooling becomes difficult to converge. In comparison, the multiple expression heads with mask filling could still produce stable results. To test if our observations on this two-head design can apply to similar scenarios, we designed another task. We built models to predict ATAC-seq signals from DNA sequences. The ATAC-seq is a technique to measure the chromatin accessibility across the whole genome. We sampled in total 100,000 genomic subregions surrounding ATAC-seq summits. Different models were trained on 80,000 DNA sequence ATAC-seq signal pairs and evaluated on the remaining 20,000 pairs. The global average pooling performed well on the model when the model is relatively small. As the model gets larger, we observed similar trends that global average pooling tend to fail on large over-parameterized models. The best performance was achieved when using the expression head design with dimension size of 128 and block size of 4. Our final Proformer model uses multiple expression heads with mask filling. It consists of two losses, an expression loss and the mask filling loss. We trained the model for the final submission by using a dimension size of 512 and a block size of 4 on 95% of the data provided by the organizers and evaluated on the remaining 5%. We used the checkpoint after the 6th epoch where the validation Pearson's R was maximized. Similar to what we saw on 10% of data, multiple expression heads with mask filling had better performance than global average polling on the validation data. We used a k-mer size of 10 and 32 expression heads. The final model has around 47 million trainable parameters. The model was implemented by TensorFlow 2 and trained on one machine with 4 A100 GPUs. We varied the learning rate over the course of training according to the formula used in the original transformer paper. We used the warm-up steps of 12,500 and the batch size of 512. The ablation analysis showed that when using only one expression head, the performance is similar to the global average polling. However, 32 expression heads with mask filling showed significant improvement over holdout validation data and produced the highest weighted scores. It's interesting that adding a GLU activation to expression heads produced even higher unweighted Pearson's R and Spearman's rho on the holdout validation data. However, the weighted score become even worse than average polling. In future, it's worth to explore different designs of the expression heads. With that, I'd like to thank the challenge organizers, all participants, members from the Quark Lab, and support from Little Heart Institute. Thank you.